Hello everyone, my name is Mahya Roustaei and I'm a research associate working with Dr. Henry at the University of Alberta. This presentation is a summary of our last project with National Research Council of Canada about the impact of weather conditions on the development of frost heave beneath railway tracks. This study investigates the mechanism of frost development within a railway embankment in a section of the Via Rail track in eastern Ontario that has experienced frost heaves during last years. You can see the damaged tie at the location of the track with largest heave as well as rail shimming of this site in these photos. Four main objectives of this study were determination of the frost susceptibility of subgrade soil layers, development of a thermal model considering different boundary conditions, evaluating the impact of culverts, developing a tool to forecast frost depth at the Smith's Fall test site. We started this study by conducting some experimental tests in order to find out the frost susceptibility degrees of subgrade soil layers. Then, a numerical model was developed in different boundary conditions, and the results were compared to what was monitored at the site. This site is an instrumented one, with piezometers, extensometers, assays, and thermistors. The only data which was used for this study was the records of these 20 thermistors, which were installed from 0.35 to 4.15 meters below the track surface. Recorded data from other instruments were also used by NRC in separated projects. We received 4 samples from different layers of subgrades. The frost susceptibility of these samples was evaluated, and the results indicated that the subgrade at this location have medium to very high degree of frost susceptibility, and the water table at this site is also within 3 meters of the track surface. So all the required factors for the development of ice lenses, which are 1, a frost susceptible soil, 2, a water source, and 3, freezing temperatures, are present at the site, and a numerical model could be a great tool to investigate the thermal regime of the embankment and potential impacts of climate conditions on the development of frost heave. Modeling was conducted using TEMP. That is a finite element software for modeling thermal changes in the ground. And this is the geometry of the model with different soil layers based on the site measurements. This model was first calibrated with the temperature records of thermistors and then used to evaluate the effect of different boundary conditions on development of frost heave. First set of results of temperature differences between ground and air temperature showed that ground became much warmer after covering by snow layer, and the effect of snow decreases when the snow cover became compacted. This is due to the changes in thermal conductivity of snow, which will increase up to 4 times when snow became compacted and dense. The exact depth of the frost line was determined from different thermal conditions to investigate the effects of different weather parameters, such as ambient temperature and snowpack on the frost line. We have 2 different cases here with no snowpack 2018-2019 and colder winter 2014-2015, the coldest weather in the last 10 years, as well as our base model and site records. These results showed that thermistors recorded the maximum frost depth of about 109 centimeters, while for TEMP model it is 103 centimeter. With no snow cover, it will increase to 120 centimeters, and in a cold winter it will be 145. Ground temperature regime of November to April at the main model showed that although the ambient temperature went up and the weather became warmer in April, a limited area in the ground was still frozen. This frozen zone, which can be extended by less snow or colder ambient temperature, will result in development of a saturated zone near surface and thaw softening phenomenon. In order to find out a better understanding of the effect of snow removal on expansion of this frozen area, 4 different cases of snowpack on the embankment were modeled as case 0, 1, 2, and 3, in which the snow cover is removing gradually, and the results showed that more snow removal results in wider frozen zone. The surface of the track at this site was surveyed 4 times by NRC using a total station to measure the absolute displacement of the rails. The survey data from February 2019 demonstrated that the entire 50 meters section of this study site had heaved, and since the maximum heave was recorded at culvert location, it became necessary to investigate the effect of culverts on the numerical result of this study. There are 3 1-meter diameter culverts at this site, located at 2 meters below the track surface and 1.5 meters distance from each other. 3 models were developed in this part of the study. 1, a cross-sectional model with 1 culvert, 2, a longitudinal model with 1 culvert, and a longitudinal model with 3 culverts located 1.5 meters apart from each other, all 50% full of water. The results showed that by adding culverts to the model, the frost penetration depth increases to 3 times. And culvert has a warming effect on the ground during summer and a cooling effect during winter. By increasing the number of culverts, we saw 10% increase in the frost penetration and 50% increase in the thickness of frozen part. In addition, in the model with 3 culverts, the soil layers at the top of culverts became totally frozen earlier than the model with 1 culvert, and although there was more expansion of frozen zone in this area in this model, but due to the warming effect of the culverts, it disappeared at the same time of the model with 1 culvert. The 4th survey measurement of this site were performed on April, which was after the thawing season, and it was expected that the track returns to its original location. But the results show that although for the most part the recorded heave were almost disappeared, there is a point in which a significant part of the heave still remained. We were curious to see what is the reason of this heave. Same as the basic model, temperature regime of culvert model showed that although the ambient temperature went up and the weather became warmer in April, a limited area in the ground was still frozen and needed more time to thaw. This frozen area is located in 3.18 meters away from the culverts, while the recorded heave of thawing season is in 3.26 meters away from the culvert's location. So this frozen zone that will totally be disappeared by May could be the reason of this remained heave. The first and second phases of this study were based on the recorded temperatures of 2018-2019 of this site, while for the third phase, the thermistors records until mid-June 2020 became available. We explored the recalibration of the model by working on the volumetric water contents, since winter 2020 had more rainfall in comparison to winter 2019, And the final model gave almost the same frost depths which was monitored at the site. The last scope of this study was developing a tool to forecast frost depth at this site. For this purpose, first, the maximum frost depth from the numerical analysis during the previous 20 years, 1999-2019, were regressed against annual freezing degree days or FDDs, and then a climate model was used to extract the FDDs of next 75 years. Using the FDDs from the climate model in the regression model, we found a frost depth penetration threshold of next 75 years. The maximum frost depth for the next 20 years is around 1 meter, which is located in the highly fouled ballast and contains 80% fine material and is a frost susceptible layer. After 2040, the maximum frost depth tends to decrease and reaches to 60 to 70 centimeters, which is within the border of the subballast and highly fouled ballast layer. The results of this study showed medium to very high frost susceptible soil at this site, development of a frozen zone in subgrade soil and near the very high frost susceptible layers, 3 times increase of the frost penetration depth at culvert location, maximum frost depth for next 20 years around frost susceptible layers. We are currently drafting a paper on this work and will make it available to those that are interested in more details. In future, we are interested in conducting this research as a precise sensitivity analysis of culvert model and investigate the effect of the amount of water in the culvert, as well as shape, depth, diameter, distance of the culverts from each other, and groundwater level of the site. In addition, we will add an insulating layer around the culvert and find out the effect of different filler materials for top of the culvert. Thank you so much for your attention, and please let me know if you have any questions.